For our second part of related rates, we're continuing with number 3. A car leaves a given point and travels north. Let's just say that it's gone y units, miles. It's traveling north at 30 miles per hour. We're assuming that this length would increase. This means that dy dt, the rate of change, is 30. How y is changing with respect to time, it's 30 miles per hour. Another car leaves the same point at the same time. It travels west, and we'll call that x. We know that north and west are perpendicular directions. We know that this rate of change, we're assuming that this is getting bigger and bigger. dx dt is going to equal 40. Then, of course, what you're going to see is there's distance between these two cars. We'd like to know at what rate that distance between the two cars is changing at the instant when the cars have traveled 2 hours. Well, right here we have a right triangle, the most famous geometry theorem in mathematics, the Pythagorean theorem. D squared, distance squared, is equal to x squared plus y squared. These are functions of time. Let's take derivatives. 2d, dd dt. D is a function of time. It's the chain rule. 2x, dx dt, plus 2y, dy dt. Divide out a 2 everywhere. That's nice and simple. We already know what dx dt and dy dt are. But as we're looking here, there is one instant that we're looking at in particular, and that's 2 hours after they've begun traveling. Distance is equal to rate times time. And if we took a look at the distance to the north, well, the rate of speed, we already know that's 30 miles per hour. For 2 hours, that's going to be 60. We can even draw a little separate picture here and say, for a brief instant, that's 60 miles. What about the distance going to the west? Well, we've got 40 times 2. Well, that's 80. So we'd have 80 miles going to the west. You might wonder what that distance is between these two cars. Well, certainly you could use the Pythagorean theorem, but I hope you see this is really a 3, 4, 5 right triangle. And in fact, it sure looks like we're multiplying all of the side lengths by 20, meaning we'd have 3 times 20 is 60, 4 times 20 is 80, 5 times 20 is 100. For this brief instant, the distance that we're going to see, we're coming right back to this derivative equation right now. We're going to say, wow, that distance is 100. Here we've got dd dt. The x length is 80. And dx dt we already saw was 40. The y length is 60. And dy dt is 30. Something we spoke about in class, something very nice. We could divide both sides by 100. If you divide by 100, you're really getting rid of 2 zeros everywhere. Look at that. You'd have dd dt is 8 times 4, which is 32. 6 times 3 is 18. And 32 plus 18 is 50. What's the rate that the distance between the two cars is changing? Well, 50 miles per hour at that particular time of 2 hours. One final problem, and then we're through. We've got a right circular cylinder. And of course, that's going to look something like so. We've got a radius. We have a height. And it says that the radius is increasing at a rate of 3 inches per minute. That's dr dt When you're increasing, you have a positive rate of change. In other words, every minute, if this were to continue, we would add 3 inches to our radius. The height, however, is decreasing. dH/dt, then, must be a negative rate of change. It's negative 2 inches per minute. In other words, every minute, the height will lose 2 inches. Find the rate of change of the volume at the instant the radius is 10 inches and the height is 20 inches. Again, here's that big word, the instant when this is going to happen. Obviously, our radius isn't always 10. Just for the briefest moment, it will be. The height isn't always 20. For a brief instant, it will be. Volume is really the area of the base, which is a circle, pi r squared right here, times the height. And at this point, it's very tempting to wonder if you did something wrong. We need to take a derivative. And I'll tell you the truth, very often you'll have more information where you can get information about the radius and the height related to one another, and you'd be able to substitute in and get an equation just with 2 variables in the end. I'm sad to say we don't get that here. When we take a derivative, we're going to have to take a derivative with the product rule on that right side. Take the derivative on the left. We get dv dt. Here we have pi, but with that product rule. The product rule is uv prime plus u prime v. I hope we're getting to a point where we don't even need to write that out. The u right here is just r squared. What's the derivative of h with respect to time? Well, it's dh dt. U prime. Well, what's the derivative of r squared? It's 2r dr dt. And what about v itself? Plain and simply, that's just h. Right now, you can plug in all of this relevant information. You can plug in your r. Here's your 10 squared. dh dt is negative 2. Here's 2 times 10 times a 3. Your dr dt is a 3. Your height is actually 20. And just cleaning this up, 10 squared is 100. 100 times negative 2 is going to be negative 200. And my goodness, as we're working through all this, 10 times 20 is 200. 2 times 3 is 6. 6 times 200 is 1200. So, of course, what we're going to see is 1200 plus negative 200 is 1000. We'll have 1000 pi. This is our rate of change for volume. So we have to have cubic inches per minute. And we are done.